Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So today we are going to discuss about the module Impatt devices, basically impact, avalanche, transit time devices from the paper Semiconductor Materials and Devices. So let us see what we are going to learn in this module. First, we will discuss a detailed operation of Impatt devices. Second, P plus N diode Impatt device operation will be discussed. Third, the doping profiles for Impatt diode will be discussed in this module. So students, let us start with a basic introduction about the module. Impact, avalanche, transit time devices are solid state oscillators or amplifiers for microwave and millimeter wave frequencies up to above 200 GHz, generally with high power output for a solid state device. Efficiencies as high as 25% have recently been obtained with gallium aluminium devices, but the transitional Impatt is a silicon device with up to 15% efficiency. So the basic principle involves 1800 phase delay of the current with respect to the voltage, which clearly will make the device exhibiting a negative resistance. Shockley in 1954 had introduced this general idea, not yet involving the impact avalanching to produce the phase shift. A number of different P plus N junctions type structures are used today. So during operation, the diode is undergoing controlled reverse breakdown. The history of the development of the Impatt device has some similarities to that of gun devices. Both were being developed in parallel in the early 1960s. For example, one Bell Laboratories group worked simultaneously on both the devices. So in the case of Impatt, there was also a theoretical prediction of one version of the Impatt operation, which was published in 1958 by W.T. Reid. That is in 1958. The event described above resulted in the first publication regarding an Impatt type oscillator, Johnson, DeLoach and Cohen, 1963. Once, only a couple of months later, red type Impatt operation was also observed. Operation of Impatt devices, the physical discussion. So let us now first discuss about the impact ionization process. Reverse breakdown is most conveniently first discussed for a P plus N diode, usually implemented with a P plus N plus structure as shown in this figure. So here the corresponding energy band diagram for a large reverse bias is shown in this figure below, where the reverse current consists primarily of holes which diffuse up to the potential barrier from the inside and then quickly traverse the junction. which are accelerated by a very strong electric field there. A small number of electrons crosses the junction in the opposite direction. Now here the smaller, because the P side is more highly doped and it is the minority carriers which constitute the reverse direction current. The holes, they will become energetic enough to be able to ionize an electron pair somewhere in the depletion layer. This process requires about 1.5 times the band gap energy, that is about 1.6 electron volts for silicon. The impact ionization will be able to sustain an avalanche if the probability that a carrier will cause an ionization event on its transit of the depletion region is equal to 1 or higher, and under these circumstances the process will start to grow rapidly in time in the manner of an avalanche. So we can express the avalanche condition as integral 0 to W alpha E dx equal to 1. Here alpha is the probability of impact ionization occurring in unit length of travel or the ionization rate. The units are usually centimeter inverse. So to be more realistic, we must recognize that the ionization rates for the electrons and holes are not the same. So the ionization rates depends very strongly on the electric field. A typical dependence is given by alpha E equal to alpha naught multiplied by e to the power 6. So a generalized avalanche condition can be derived for the case of unequal rates for electrons and holes. That is, we can write integral 0 to W beta multiplied by exponential of minus integral 0 to infinity over beta minus a dx prime, this bracket close, the integral over dx equal to 1. So we define the average ionization rate for electrons and holes to be as alpha is approximately equal to beta exponential to the power minus integral 0 to infinity beta minus alpha dx prime, which leads to integral 0 to W alpha dx, the average alpha, equal to 1. So by using above these equations, the effective alpha can be shown to be alpha effective equal to k minus 1 multiplied by alpha by ln k. Now here k is beta by alpha. So this value of the average alpha can be used with very accurate results for gallium arsenide. Now, due to strong dependence on the electric field, we find that the avalanching occurs almost exclusively very close to the peak of the electric field. So this region of the diode is termed as the avalanche region. In a device with field distribution which is discussed previously in the figure, the holes generated will drift to the left into the contact and will be out of the picture as far as the device operation is concerned, whereas the electrons, they will drift to the right through the so-called drift region of the device as shown in this figure. Reverse breakdown voltage. It is convenient to observe that the maximum field of the triangular field distribution in a PN junction diode at breakdown is fairly independent of the doping and the type of junction. The explanation for this fact is again the very high electric field dependence of the ionization coefficient Q. Thus, when the field has reached a certain magnitude, then it becomes very easy to satisfy the avalanche condition when the integral is taken over typical junction widths, and the field for which this happens is basically a universal constant for the material. So the reverse breakdown voltage can now be derived in terms of the maximum electric field at breakdown, that is EM. So the results are for the standard cases of a one-sided P plus N diode and the two-sided respectively, and these are VB equal to half multiplied by EM multiplied by W equal to epsilon S EM square divided by 2E NB, and for VB for the two-sided diode is equal to half EM multiplied by W equal to epsilon S EM square by E multiplied by NB. Note that the breakdown voltage is inversely proportional to the doping in both the cases. Typical breakdown voltages are in the range of 10 to 100 volts range and are obtained if the doping is of the order of 10 to the power 16 to 10 to the power 17 centimeter minus cube on the low side in the one-sided junction. These widths are 10 to 20% of the width of the entire depletion region, justifying the model which assumes that the drift region occupies most of the depletion region. Students, let us now discuss another parameter, that is a saturation drift velocity. The saturation velocity decreases as the temperature increases. It is important that the velocity is almost independent of the electric field for the high fields which exist in Impatt devices. This means that we can regard the carrier velocity as essentially constant and equals to the saturation velocity anywhere in the drift region. So the saturation velocity of electrons and holes in gallium arsenide is somewhat lower. So the saturation velocity is essentially the same for electrons and holes, and its temperature dependence is given by Vst equal to 6.12 multiplied by 10 to the power 6 bracket 0.268 plus 262 by 273 plus t minus 1.21 multiplied by 10 to the power 4 divided by 273 plus t the whole square, where Vst is in centimeter per second and T is in degree Celsius. Displacement current. Due to the large amounts of rapidly moving electric charge in an Impatt device, it is necessary to take the displacement current into account. So here the avalanche, it gives rise to the injected current which is localized to the avalanche region. So due to the nature of the avalanche process, the injected current is concentrated towards the end of the first half period of AC voltage across the device. The time dependence of the injected charge is therefore similar to a short pulse. As this pulse of charge drifts through the drift region, we can model it with a constant charge which is moving through a capacitor. So students, the total current is continuous in general and it is represented by a displacement current in any plane of the capacitor which does not contain the charge as shown in this figure. If the charge is moving with constant velocity, then the total current is also constant in time until the charge has traversed the capacitor. So we can now calculate the average current when the charge Q moves through the capacitor of width W in a time delta t is given by I equal to Q by delta t equal to Q multiplied by V divided by W. So if the velocity of the charge is equal to the saturated velocity Vs, then the current becomes I equal to Q Vs by W. P plus N diode Impatt device operation. So students, let us now discuss its operation and the schematic of the Impatt device or the basic process behind its operation is shown in this figure. Now here we assume that the electric field consists of a DC component adjusted so that the reverse breakdown just occurs, and an AC component which is added uniformly across the device. So the structure of the device is shown over here, and the electric field and voltage are positive when they accelerate the carriers in the positive Z direction, and the current is positive in the same direction as that of the electric field. Now referring to the previous figure where the AC electric field is shown in the lowest set of curves as a function of time, in the top of the diagram we can see that in the first frame the DC electric field distribution, or we can say in this figure below you can see clearly, as the AC field component grows positive, the avalanche is initiated. So the growth of the charge produced by the avalanche is pictured in the second set of frames from the top. In the second frame, The AC field is at its maximum, that is at T equal to capital T by 4, but the maximum avalanche charge injection does not occur until the third frame, that is when T equal to capital T by 2, just before the AC voltage goes negative and drives the total voltage below the breakdown voltage. In other words, we can say that the avalanche continues to grow as long as the electric field is larger than EM. As the AC voltage becomes more negative, the avalanche injected charge drifts through the drift region, and the device current shown in the next set of frames is constant with time until the charge reaches the right contact. So students, if we compare the two lowest set of frames, we notice that the current has an approximately square waveform, being off for the first half period and constant and positive during the second half period, which represents the negative resistance which we sought. The negative resistance arises as a result of three effects. First, the delay of the maximum of the avalanche until it just turn off, that is by T by 2 with respect to T equal to 0. Second, the transit time delay of T by 2 for the drifting charges in the drift region. Third, the effect of the displacement current, which produces a square current pulse from a short pulse of the injected charge. This factor effectively speeds up the onset of the current in the contact by T by 2. So taking into account all of the three above effects, we find a total delay of T by 2 of the current with respect to the voltage. So specifically, we see that the correct value of the transit time delay in the drift region should be about T by 2. So students, we can also calculate the estimated frequency of operation as follows. So note that there is a factor of 2 ratio of the transit time in periods for the Impatt device compared with the transit time mode gun device. Tau T equal to T by 2, which is equivalent to 1 by 2F equal to WD by nu T. So your F equal to tau T divided by 2 WD. As an example, a 10 GHz Impatt device using silicon should have a drift region length of about 5 micron. We also find it useful to introduce the concept of transit angle, which is defined as theta d equal to omega WD by nu s or nu t, which is equivalent to omega multiplied by tau t. Let us now discuss the doping profiles for Impatt diodes. A great variety of doping profiles for Impatt diodes, and a few, they are illustrated in these figures. The recent trend has been towards the structures with very narrow, means higher efficiency, avalanche regions, such as the profile originally proposed by Reed 1958. The low-high-low structure has a uniform field in the avalanche region, while the narrow clump of the charge, basically donors, allows the field to decrease to values well below EM immediately as the carriers enters the drift region, preventing any avalanche there. So another popular structure is the double drift one, which allows both the electrons and holes to drift through the separate drift regions. So students, as you can see in the first figure, we have the distribution of the doping, the electric field and ionization probability in a Reed type Impatt diode. In the second figure, which again shows the distribution of doping, electric field and ionization probability in a P plus N single drift diode, and the second one is P plus P N N plus symmetric double drift diode. The last figure shows the distribution of doping, electric field and ionization probability in a Impatt device with high-low structure, and the second one shows the Impatt device with low-high-low structure. So students, let us summarize what we have learnt in this module. First, the operation of Impatt devices, that is the impact ionization process, reverse breakdown voltage, saturation drift velocity and displacement current were discussed. Second, P plus N diode Impatt device operation was also discussed. Lastly, the doping profiles for Impatt diode was discussed. Thank you.